Okay, so to continue from what we left last time, if you recall, we talked about the stationary m-dependent sequence, right? So the main theorem we obtained is about the asymptotic distribution for an average of a sample that's drawn from this m-dependent sequence, stationary m-dependent sequence. So specifically, we have this fixed m, which is known. And we have x1, x2. This random vector sequence is stationary and dependent. So what we know about this stationarity is that x1, x2, and xi, they must follow the same identical distribution. That's just implied by the stationarity. But here we drop that independence and replaced it by the m dependence. So this is looser than independence, because what it means is that if we set m equals to 0, m dependence reduces to independence. But this can be greater than 0, then we may have independence for two random variables if their distance or gap is less than m. But if it's greater or equal than m, then they're independent, essentially. So here, for this sequence of random vectors or random variables, we have expectation xi equals mu. Okay. And by the way, this is about random variables. I should be more specific. So here mu is a scalar, and the variance xi is sigma squared finite. Okay. So then the theorem, or what we derived last time, if you recall that proof, we divide the sequence into segments of k length, then m length, then k and m, right? And we try to first fix k, let n go to infinity, so the number of segments will be infinity. But then with that asymptotics from central limit theorem, we let k go to infinity. That's what the proof we did last time. So with that lengthy proof, the conclusion we get is very simple. It's this. This form we're familiar with, the same as what we have in central limit theorem. It converges in law to a normal distribution with mean 0. The variance, if it's central limit theorem, it's just sigma squared. But here we have some dependence. So we will add those covariances here. 2 times k go from 1 to m, gamma k. That's it. So in other words, we keep the dependencies if the random variables are within a gap of m. So in other words, say gamma k is basically the covariance, where gamma k is the covariance of x1 and x1 plus k. That's what we mean by gamma k. Okay, so we had this result last time. Today, we're going to come back to 2 motivating examples for the stationary m-dependent sequences. And those 2 examples we've shown to you before. Now we're going to see how we can apply this theorem to those 2 examples and derive the asymptotic distribution of xn bar. So example 1, if you recall, we started with x1, x2, IID, the simple case. But the statistic or the random variable we are interested in is not a simple average, but it's this. I from 1 to m, xi times xi plus m. So it's this product, okay, product moment. And we multiply pairs that are m away from each other. Okay, and for this IID sequence, we have mean, mu, variance, tau square. We have this. So then how do we derive this, right? So here, to use this result, we are going to, so we want to know what's its asymptotic distribution. That's the question we want to solve here. So to solve this problem, we are going to rewrite this Sn as a form of average, right? We have average here, this is a sum. But inside the sum, the entries are not IID. So we are going to define each entry as yi. Xi times xi plus m. Okay. Then, so this yi is the xi in our theorem. Okay. And then let's look at its mean. Expectation. Okay. Expectation xi plus m. Because of independence, right? IID. So it's equal to expectation of xi times expectation of xi plus m. And that gives me mu squared. Okay, I have that EYI, expectation yi. How about variance? That's what we need in this result, right? We need this mu, we need this sigma square, and we need all the gamma k's. So variance of yi, what is that? So for this, we can use the definition of variance, right? Because we want to use the moments to help us calculate it. Expectation of yi square minus the square of expectation of yi, right? We use this formula. And then what's expectation of yi square? It's xi square times xi plus m square. And this we already know, mu square and square again. So minus mu fourth. And for this one, we're going to use the IID again. So it's equal to expectation of xi square, right? Then square minus mu fourth. And for this one, what is that? Expectation of xi square is equal to its mean square plus variance. So that's equal to mu square plus tau square, then square minus mu fourth. Okay, and that will leave me with tau fourth plus 2 tau square mu square. That's the variance of yi. And what's left is this gamma k here. So do we have m-dependent sequence? Yes, we do. Actually, if you look at it, right? So we would have, you see, yi is xi times xi plus m, I plus m. And then yi plus m would involve xi plus m again. Right, so they share one random variable, but after that, all the following y something will share nothing with this yi, so they are independent. So that's why we only have dependence between yi and yi plus m. So what this implies is that if we define gamma k as the covariance of yi plus k, right? With this definition, then we can easily see y1 to ym minus 1. Suppose that m is greater than 2, okay? So greater or equal than 2. Then these are all zeros because you can see that in this case, yi and yi plus 1 don't share anything. yi plus m minus 1 also don't share anything. But gamma m is the only place where they share something. It's the covariance of yi plus m. Again, we're going to use moments to define covariance. So it's equal to expectation of yi plus m minus expectation of yi times expectation of yi plus m. Okay, And then what is this? We can use the definition of yi and write it as xi times xi plus m squared. It's in both terms, and times xi plus 2m. And for the second term, we already have it. So that's what here, minus mu fourth. Okay, for this one, we are going to use independence again. So it's expectation xi times expectation xi plus m squared times expectation I plus 2m. Okay, and what is this? So these two terms can be combined because they're both mu squared. And what's in the middle, we already derived. It's here. It's actually expectation of xi squared is equal to xi's variance plus the square of expectation of xi. So it's here. So times mu squared plus tau squared, okay, minus mu fourth. So we are left with mu squared times tau squared. All right, and also after that, you see, we have zero covariance, no more dependence. So with this, then we put it back, right? So therefore, by that theorem, we have root n times the average. Here, the average is just equal to Sn divided by n minus the mean of yi, that's mu squared. Okay, this will converge in law to a normal distribution with mean 0. The first is the variance of yi, that's this term, tau fourth plus 2 times tau squared mu squared. That's the variance. Second term is 2 times all the sum of covariances, and we only have one term, gamma m, mu squared, tau squared, right? So you see, clearly these two terms can be combined. So I get 4 here. That's the result. So essentially, we derive the asymptotic distribution for this Sn using this theorem. And you can see in the result, we only have the parameters we know. That is mu, which is the expectation of xi, and tau squared. That's the variance of xi. Okay, so for those of you who are interested in checking how this result works numerically, actually you could simply do something on your computer. For example, you can just generate IID by sampling from a common distribution. You could try, normal is the simple thing, right? If it's normal, then it will be the perfect. But if it's not normal, you can try Poisson, or you can try uniform distribution even between 0 and 1. And as long as you know the actual distribution, you can know what's the mu, what's the tau square, and then you just do this calculation. As long as n is large, you have this Sn, right? So what you can do is that with an n set, say 100 or 1000, you repeat this simulation and you will get, each simulation will give you one value of this Sn. And then you just plot the distribution of this Sn divided by n minus this times square root of n. And you can see whether the distribution you observe from multiple simulations look like normal. And you can have this theoretical distribution based on the formula, and you can have that numerical realization. So I think it's a nice try so you can understand what we're saying better. So essentially, based on each realization, we only get one value, one realization of Sn. But what we're talking about here is the distribution of the possible realizations. Okay. So that's example 1. Do we have questions? It's a simple application of this formula. So it's theorem. So we just show you how we can do this in practice. Okay, so now if no question, we'll move on to example 2. So example 2, if you recall, it's about that Bernoulli thing. So here, we are having x1, x2 following IID Bernoulli with success probability P. Okay, so 1 means like a head, 0 a tail, and this is the probability of getting a head. And then the statistic we are interested in, it's called Tm. Okay, I'm going to erase the remaining part. Okay, so the statistic we are interested in is the number of sequences of ones. Number of segments of ones. Okay, so we talk about what it means. So if you recall, we are just doing this, right? So mathematically, we can write this Tn as the summation. I goes from 1 to m, and indicator function, whether a segment of ones starts at I, at xi. So to do that, if you recall, we can write this out as for the first x1, if it is 1, it must be a start of a segment. Otherwise, it's not a start. After that, to call xi as a start, we need xi minus 1 to be 0, while xi to be 1. Starting from I equals to 2 to n, we need xi to be 1 for sure, but the previous one to be 0. So we write 1 minus xi minus 1. Okay, so that's it. So again, you see we are having a sort of a sum, right? And for this sum, we need to play with it so we can sort of transform it to this xm bar in our theorem. That's still the plan. So to do that, here we are going to worry about this sum. This is just one random variable and we'll deal with this later. Okay, so let's say we define in our solution, we define yi to be equal to, okay, xi plus 1 times 1 minus xi. So in this case, I will start from 1 to m minus 1. That's my yi, my new sequence. So what is the, so this is a stationary sequence because of this IID of x1 to xm. So it means that no matter where I start, right, yi will have the same distribution as yi plus 1. And also, if I look at yi plus 1, yi plus 2, that joint distribution, it will be the same as, say, yi minus 1 and yi's joint distribution because of this IID. That's nice. And regarding the m dependence, what is the m? It's very clear that we only have overlap between two adjacent yi, right? Yi and yi plus 1 would share xi minus I plus 1. So they will share. But after that, yi and yi plus 2 will share no random variables. So therefore, here the m is 1. We have m dependence or 1 dependence. So therefore, let's do our calculation. What is expectation of yi? It's very obvious. Just expectation of xi plus 1 times 1 minus xi. Now the IID will help us again. Because of independence, we can write it as the product of two expectations. So then it's obvious what p times 1 minus p. That's the expectation of yi. And we also need the variance of yi. So we'll move here. Or yeah, we'll move here. And again, we are going to use the definition of the variance based on the moments. So we will have expectation of yi squared minus the square of expectation of yi. So then, what is the expectation of yi squared? Okay, so look at it. One thing, we can simplify a little bit. Instead of just saying, okay, yi is this, right? We get a square of this inside. That's doable, but we can do this in a simpler way. Think about yi. Is it still binary? 0 or 1? You can only take two values. Yes, right? If it's binary, then we know its square is just equal to itself, right? 0 squared is 0, 1 squared is 1. So therefore, this can be simplified as this, because y squared equals yi, okay? And for the second term, we know it already. So therefore, we would have, right? That's the second term, but this is just that's the variance of yi. How about covariance? For covariance, we just need to worry about gamma 1. That's the covariance of yi and yi plus 1, right? That's what we have. And again, we're going to use the moments. Expectation of yi times yi plus 1 minus expectation of yi times expectation of yi plus 1. And they're equal, we know that. So for this, we are going to use the definition. So for this expectation of yi times yi plus 1, what do we have actually? Actually, we don't need any calculation, it's obvious. So you see by the definition, when yi is 1, okay, so when yi is 1, then yi plus 1 must be 0. The reason is that when yi is 1, xi plus 1 must be 1. And then what is yi plus 1? By definition, it's xi plus 2 times 1 minus xi plus 1, right? So when this is 1, then this is 0. Then yi plus 1 must be 0. So therefore, by the definition of this run, the segment starting position, then so if this is a start, right? So then we know that the previous one is not a start and the next one is not a start. Okay, does that make sense? Yeah, this is the nature of this definition. So therefore, this must be 0. And this is what we know. All right, so putting things together, you see, we are able to do something. That is, if we take this y1 to yn minus 1, right? So we would actually be able to see that we use the theorem. But here, one thing I want to say is that this n minus 1 is not something to worry about because we'll let it go to infinity. So therefore, being n minus 1 or n doesn't matter, right? So therefore, by the theorem, what we have is root n times yn bar. So I'm using this y1 to yn's average, is yn bar, minus its mean. Its mean is here, p times 1 minus p. This quantity will converge in law to normal distribution with mean 0. And in the variance, we need the variance of yi, which is here. Okay, so p1 minus p minus p squared times 1 minus p squared. Okay, plus 2 times this, okay? Plus 2 times this, and this is negative. This minus 2 and this minus 1 can be combined because they're both of the same term. So minus 3. That's it. So again, this is something you can check using your numerical simulation. But we're not done yet, right? This is only about yn bar, but we want to have this Tn. And we know that they have some tricky relationship, right? So essentially, you see what we have here by this yi definition. This is just equal to, let's see, x1 is left, and here is just times n minus 1 times yn minus 1 bar, right? We only have the sum that go from y1 to yn minus 1. Okay, so, but this is something we could actually show that it doesn't matter that much because we need to have this, okay, so to make it work, right? So we need to divide n minus 1 square root from here. So maybe I'll put it here. So Tn equals x1 plus summation I from 1 to n minus 1, yi. Okay, so this is equal to x1 plus n minus 1 times y bar n minus 1. Okay, and as I said, for asymptotics, n minus 1 and n are basically the same. So therefore, in this result, I can change n to n minus 1 without a problem. Okay, and then what do I have here? So to create this form, I need to divide root n minus 1 from each term. Okay, equals to that's what I have. And so therefore, you see, to recreate what I have there, I'm almost there. So I would have Tn divided by root n minus 1, okay, minus x1 divided by this, and what? I would have minus root n minus 1 times p times 1 minus p, this term. This whole thing would converge in law to this distribution. Minus 3p squared. Okay, so I have that. But you see, what I can simplify this for is that this term, you know, I don't need to worry about it anyway, because this term will go down to 0 in law and also in probability, because this x1 is binary, right? And this is going down, the n minus 1 is going to infinity. So I could cross this out. And to simplify my form, as I said, n minus 1 and n doesn't matter. I can change this to n. I can change this to n. So therefore, if I do that, okay, so what I will have is finally is this form. So this left-hand side can be, okay, I can simply write it as root n, that's the denominator. The numerator is Tn minus mp 1 minus p. Okay, this thing will converge in law to this normal distribution. So in other words, asymptotically, you see, this Tn by itself its mean is going to converge to this NP times 1 p. So as the larger the n you get, the closer these two things will be. And also, you see, P will actually be in the success probability will be in this variance term right here. Okay, and I think you can play with this and look at, you can think about, by playing with this function, a function of P, you can think about when the variance is big, when the variance is small. So clearly, when P is 0 or P is 1, we're going to have a, we call this degenerate case, this variance 0. So when this happens, as we'll see later, then this asymptotic distribution doesn't mean much, right? It doesn't give you a distribution. It just tells you, okay, this is convergent to that. That's not good. But in that case, we can go to another order, which we'll see later. So to deal with that case, but for P greater than 0, less than 1. So we can see that, we can check how this train will look like. So in other words, that will tell you about the accuracy of this distribution, or the accuracy of this Tn, or how far away it is from this value in this asymptotic distribution, the spread. Okay, so that's all I want to say about the applications of this theorem. So compared to our central limit theorem, the main difference is the consideration of the covariances. But because we have that m dependence with m being finite, then we don't need to consider all possible covariances, but only covariances of gaps up to m. Does that make sense to everyone? Okay, great. Okay, so you can see that the results we gave you so far, central limit theorem, Limburg-Feller theorem, this m dependence, so they are all kind of related to our variance of the central limit theorem, right? So to summarize, the central limit theorem is telling us when we are looking at the sample mean and when the sample size is large enough, then even though my random variables, the IID random variables may not be from a normal distribution, but we can use a normal distribution to approximate the distribution of this large sample mean. That's what it says. So then we may wonder how close this distribution is to the normal, right? So we know that it's convergent to normal, but we want to know what's the rate. And also, given a finite m, what's the difference between x m bars this term's distribution and the normal distribution? So to address this question, we have this important result called the Barry-Essen theorem. So it just addresses the problem I described. And we will formalize it. Okay. So let's say that we again start from our familiar setting. x1 to xn, IID with mean mu, variance sigma square. So to facilitate our discussion, we first standardize each xi. We subtract the mean and divide the standard deviation. So with the standardization, then clearly, you know, yi will have mean 0 and variance 1. Okay. So therefore, in our central limit theorem, if we apply it to y bar, yn bar, you know, central limit theorem says root n times yn bar. There's no need to subtract the mean because it's 0. We converge in law to standard normal, right? This is what we have from central limit theorem. But what Barry-Essen talks about is about their distance. So what it does is that it defines the CDF. Let Gn, okay, be the CDF of roots n yn bar. What does that mean? It means, let's say we have a real value, then Gn evaluated at the real value is defined as the probability that root m ym bar is less or equal than that real value. This is what it means. The standard definition of CDF. Okay, and we denote this capitalized phi is as the CDF of standard normal. This is standard notation. Okay, so we are interested in the difference between those two CDFs. So one thing we know actually by the central limit theorem is that we know these two things were getting closer and closer together. So basically we have that the difference, okay, g n x minus phi x at any real value x, and we take the sup of x. We take the sup, and this sup will actually go down to 0 as n goes to infinity. And this is actually ensured by the pointwise convergence by this convergence in law, as well as, you know, the convergence in law, it implies pointwise convergence, right? G and x will converge to phi x, right? That's what we have from central limit theorem. But this makes it stronger sup. It's more like we have this whole thing uniformly converge to 0. And to show that this is very similar to what we have seen before, the Glivenko-Cantelli theorem, right? That's also about the sup. But recall that it's not about this. It's actually about, let me put it here. It's actually about empirical CDF. In that case, we have this Fn hat x minus the Fx. So this is the population CDF. This is the empirical CDF based on our sample. And that's different because over there, this is a random function. Just be careful. This is a random CDF. The randomness comes from our random sample. So therefore, when we talk about this thing goes to 0 as n goes to infinity, we talk about it in the probability sense. We say that this happens with probability 1, or we say this happens almost surely. It's the same thing. So you see, because here this is a random CDF, while compared to here, going back to CLT, the central limit theorem, there's no random function, okay? This is a fixed deterministic function. This is a deterministic function as well. So I think I'll use this as an opportunity to explain the importance of randomness in our statistics research. Okay, so therefore, we have the similar form, but there's no randomness here. So we don't need to say almost surely or with probability 1, but we need to say the mode here. All right, then coming back here, right? This is a result of pointwise convergence by CLT and the boundedness of the CDF, because all the two CDFs are bounded between 0 and 1. So that's why we have this result. But Barry-Essen goes one step forward. It tells us not just this going down to 0, but at what rate. So Barry-Essen right, what this says is that sup between the absolute difference between g and x and this big phi x is bounded by some constants times the third moment, absolute third moment, and divided by root m. So this is the key. So you know, this is actually in our central limit theorem, we don't talk about the third moment. There's no requirement of third moment, just on the finiteness of the second moment, right? But this, to get obtain this bound, we need the third moment to be finite. And also we see clearly the rate is root m. So it just tells us the worst case, right? For the worst x, their differences is as large as some constant divided by root m. So that's the Barry-Essen theorem. So in other words, I think it's useful if you want to make some approximation, right? If you want to use standard normal CDF to approximate the CDF of your standardized sample mean times root m. If you want to do that approximation, then your approximation error is of the order 1 over root m. So you can get a sense about how large it is. For example, if your sample size is 100, right, then 1 over root n will give you 0.1. That's about the error. Okay, so this is first thing I'm going to introduce some used result that we should know. Then another interesting result is called the Edgeworth expansion. Okay, so what this does is trying to write g and x to expand g and x in terms of phi x and some remaining terms. Okay, so first of all, let me just introduce some notations. So gamma, I'll introduce, don't confuse this with the covariance gamma k we use. This is a different gamma. Is the third moment of yi. But this is the third moment without absolute value, but that's the absolute value. And when we got to give this a name, skewness of the distribution of yi. Right? So we know that if yi has a symmetric distribution, this should be 0. 0 if yi has a symmetric distribution. Okay, and we also have the fourth moment, tau. And we call this kurtosis. This is related to the heaviness of the tail of the yi's distribution. Okay, and we suppose this is finite. So therefore, the Edgeworth expansion takes this form. So basically, I'm just going to write it out. We have the first term, of course, the main term. That's the CDF of standard normal. And the second term, interestingly, it takes the form skewness times the argument, where we evaluate the CDF at the x squared minus 1, divided by root n times 6. And this is the density function of standard normal. Is the PDF, probability density function of standard normal. Okay. And then we have another term that involves the fourth moment tau and the third moment gamma, but I'm not going to write it because it's pretty long. So you just know that it's some term times, okay, I'll just put it here, some term f function of tau, gamma, and x. Okay, I'm just ignoring it. But the key is that it times is of the order 1 over n. Okay, 1 over n is here times phi x, or probably I just put 1 over n here. Yeah, I'll just put it here, ignore some constant. And then finally, the remainder small o 1 over n. So I think what's worth looking at or what's worthy about this expansion is when your random variable yi, right? The random variables you are interested in are symmetrical. It have a symmetrical distribution. When that happens, then we said, okay, gamma is 0. Then this term goes away. And that's very nice because once you have this term goes away, you would just be with this 1 over n term as the difference between this actual CDF and the normal approximated CDF, right? So 1 over n is much smaller than 1 over root n. Just as my old example, if your sample size is 100, then 1 over n give you an error of 0.01, but this is 0.1. So you see, that's why it means that the central limit theorem converges faster if our original random variables have a symmetric distribution after standardization. Okay, so that's pretty much it. And so the Edgeworth expansion is very useful for theoretical analysis regarding the convergence rate. So as I said in the note, so there was a very famous statistician who used to be in UC Davis in Australia, theoretical statistician Peter Hall. And he was very productive. And one of his very famous work is about use Edgeworth expansion to analyze the bootstrap procedure. Like how well does bootstrap work, which we'll try to finish, I think, covering the last part of our class. Okay, so that's it. So these two are just very useful results about univariate central limit theorem. So this is the case where our x1 to xn are random variables of 1 dimension. Okay, do we have questions? Okay, so if not, then we will move on to a new topic, a very useful series of theorems for working with convergence and law, right? Since we have been talking with convergence and law for multiple lectures already, starting from the central limit theorem, right? We will give you some useful results so you can generalize what we have. So this is called, the series of theorems called Slutsky theorems. So it's 3 useful results, and we will give you them one by one. So the first one is also called continuous mapping theorem. So this is about, given you already have a convergence in law, what if you apply some continuous transformation or continuous map to your random variable sequence and the limit? Do you still have the convergence in law after the transformation? This is it. So let's make this more general, back to the vector form. So let's say that we have xn in Rd, d-dimensional, and xn convergent law to x. Of course, x is also d-dimensional. And this function f, that's a vector value function, maps from Rd, say, to Rk, such that our limit random vector is in the continuity set of f. The notation I've seen before with probability 1. So in other words, we don't need to worry about the discontinuity points of f because all we care about, the limiting random vector, only has probability masses at where this f is continuous at. Okay, so then the conclusion is very straightforward. Fxn, now this is k-dimensional convergent law to fx. Okay, so that's why we call this continuity mapping theorem. And the proof here is actually very straightforward with the powerful tools we have, the Halibri Theorem, and we are going to use that to show it. Okay, so if you recall, in the Halibri, I think it's statement C. In statement C says that if for any continuous bounded function g, we can have expectation of gxn converge to expectation of gx, then we can say xn converges in log to x, right? We have that equivalence, and we're going to use that. So by Halibri, so with that g, okay, we are going to apply g to what we need to prove here. Let g from Rk to R be bounded and continuous. Okay, so by this Halibri, it is sufficient to prove that the expectation of g applied to our target fxm would converge to expectation of g applied to the limit fx. As long as we can show this, then we can show fxn converges to fx in law. Okay, how do we show it? We are going to use here f, right? So clearly you can see that let this h function be the composite function of g and f. So that means h, we first apply this an RD vector into f, then fx into g, right? So you can see that then this composite function would be a map from RD to R, right? So you can see that because g is a bounded function, then h must be a bounded function without a problem. And also g is a continuous function. So whenever f is continuous at, h must be continuous at, right? That makes sense. So therefore, you see, we would have, so then h is bounded, okay? And because h has the same domain as f, right? So whenever a point is continuous at f, it must be continuous at h. So we can say that the continuity set of f is contained in the continuity set of h. Okay, so therefore, you see, by the fourth, I think, statement D of Halibri, we would have, so maybe I'll just say by Halibri statement C, just to make it clear for you. By Halibri statement D, okay? We have, so you see, we have this x in CF equals 1. So we would have x in CH also with probability 1. Okay, that allows us to use the Halibri last statement, which only requires boundedness, right? Not continuity, only measurable with this condition, this limit in the continuity set with probability 1 condition. So therefore, by this, we would have xn converging log to x imply that expectation of hxm, the h function here, converge to expectation of hx. Okay, with this, that's basically this, right? H is just G composite F. We have this. Then this will let us use Halibri statement C to go back to what we need, fx and converging log to fx. So we use Halibri for twice. And we look at two different functions. Even though it's the same thing, But when we go from convergence law to convergence expectation, we consider the H function, which is bounded but not necessarily continuous. When we go from convergence in expectation to convergence in law, we look at this G function, which is continuous and bounded. Okay, does that make sense? Okay, so Halibri is a very powerful tool. Now you see that. Okay, so that's the first Slutsky theorem. It's very useful. Continuity, right? So that will give you some good assurance. That means if you have central limit theorem to start with, if you apply some nice continuous function to the xn bar, the sample average, then you still have convergence in law. You just need to transform the other side by that same function. So this in the central limit theorem follows normal distribution, but after the transformation, it may not be normal. For example, if x follows standard normal, then x squared would follow chi-square 1. But that will still give us some good asymptotic distribution. Okay, first statement. Now statement B. It's the theorem B. Okay, so this is also very useful. Okay. So it allows us to transform convergence in law from one sequence to another sequence. As long as the two sequences are becoming gradually indistinguishable as n goes up. That's pretty much it. Okay, so actually, if you recall the proof we used in our last theorem, in the last lecture regarding the convergence or regarding the m-dependent stationary sequence, regarding that theorem, we had a lemma sort of similar to this, but that's actually a little more complicated because in that lemma, we involve n and k, two things that goes up to infinity. But this is just about n, okay? And how do we prove this? So I'm going to quickly go over the proof because I think it's something similar to what we have seen before. When we look at something goes down to improbability to 0, we always want to divide it into two cases, larger than, so this thing larger than some delta, or this thing greater than delta, right? So we want to use that probability of this thing being greater than delta going down to 0. We are going to use that property. So again, to prove this, we are going to use the Halibri as well. Okay, so for this one, we're just going to use the Halibri statement B. So we're going to let G be continuous and has a finite or has a compact support with a compact support. Outside of the compact set, its value is 0. Okay, so with this, if we can show that expectation of GYN converges to expectation of GX, we're done. Okay, so because this G, we know this is special case of the bounded continuous. So we know this is uniformly continuous. We used this before. So it says that for any epsilon greater than 0, we can find whether exists a delta such that whenever x and y are within delta distance, we have gx minus gy are within epsilon distance, right? This is what we have for the uniform continuity. Okay, and also G is bounded. right? So let's assume for general, gx is less than b. Okay, that's the boundedness. So therefore, to prove that Halibri, we look at the distance between expectation of gym minus expectation of gx. We want this to go down to 0. And to make use of this condition, we need to introduce xn in the middle, right? Xn is our condition. So by the triangular inequality, we have expectation of gym minus expectation of gxm plus expectation of gxm minus expectation of gx. Okay. So, right. So then we need to deal with this part. This part is actually easy. By the condition, we know as n goes to infinity, this will go down to 0 because we have x when convergent log to x by Halibri. We have that. Okay, by Halibri on statement B and xn convergent log to x. So we need to worry about the first part. The first part, we are going to use this interesting thing. So we have seen this before. So again, we're going to apply triangular inequality here again. So, or actually we don't need that. Actually, we just need to write this, okay, this part. For this part, I'm going to write it into two cases as about how far away xn and yn is, whether they are within delta neighborhood or not. Okay, times the indicator. Maybe I should use the upper bound, sorry. Okay, this is something I need to correct. I think this is something I need to correct in my notes, sorry. So this should be less or equal than expectation of this gym minus gxm. I move the expectation inside, and that will give me an upper bound. Okay, times the indicator that xn minus ym is less than delta. Okay, that's the first term. And I will have another expectation. Again, absolute gym minus gxn times the indicator xn minus yn greater or equal than delta. Okay, I have these two expectations to deal with. And for the first expectation, I'm going to use that uniform continuity. I know that when this indicator takes value 1, then this absolute difference must be less than epsilon. Okay, so therefore, I get epsilon as its upper bound. And for the second term, I'm going to move this part out by the boundedness b. So it's no greater than 2 times b, right? Each one is no greater than b. So their difference cannot be greater than 2b times the probability xm minus ym greater or equal than delta. Okay, again, we can use that convergence in probability to 0 for the difference. So this term will go down to 0 as n goes to infinity. So then you can see for this difference I care about, when n goes to infinity, it's upper bounded by epsilon only. And epsilon is any epsilon I set. So I can let epsilon go down to 0 and I'm done. So therefore, to conclude, we prove that expectation of GYM minus expectation of GX, their absolute difference is going to 0 as n goes to infinity. Then by Halibri, we would have Yn converge in law to X. So again, I think Slutsky theorems are very nice applications for you to see the power of Halibri, why it makes things a lot easier if you can prove just the convergence in expectation. And this trick is very popular, or is very widely used. When you have some convergence in probability to 0, you try to divide into 2 cases. Okay, so do you have questions for this part? Yes. Mm-hmm. Oh, you mean here, this part? Yeah, actually, we can change this to convergence in law, because we said that when the limit is a constant, then convergence in law implies convergence in probability. Yeah. So yeah, it's okay. We can just relax this. Yeah. But still, this, even if we relax it, our proof will still use this convergence in law. Yeah. Convergence probability. Okay, so the last thing, which is that's also very interesting. So the third Slutsky theorem, C. Okay, let me try to finish this part, the indication. What does this imply? Tell us. So this means that if we want to prove something convergence in law to a limit, right? Or if we want to derive the asymptotic distribution of some sequence, but it's not easy, we can find an alternative or surrogate xn. So as long as we can derive this easily, it's asymptotic distribution. And as long as we can show that their difference are going down to 0, then we're good. Right, so this gives us an idea about how to derive the asymptotic distribution for some difficult sequences. Okay, so last one, it's about the coupling of 2 sequences. So we have xn, d-dimensional, yn, k-dimensional, and we have xn convergent law to some x, random vector, ym convergent law to some constant vector c. Okay, so one has a random limit, one has a constant fixed limit. Then when we do the coupling, we can say that xn, yn jointly will convergent law to this coupled limit. Okay, so it's actually very useful because you see, if you consider this as their separate distributions, or if these 1, k is 1, we call marginal distributions, and this is about their joint distribution. And actually, I have to say that this doesn't hold in general if C is random. Okay, if we change this to Y, it doesn't hold. And we'll talk about that later, because you can see that the dependence structure between X and Ym may be different from the dependence of X and Y. But this marginal convergence law doesn't talk about dependence at all. However, when this C part is a fixed constant vector, then there's no worry about that dependence. Okay, so how can we prove this? Actually, for this one, we just need to show it using that statement, that theorem B. It tells us already. So, what we can say is that this xn, so we'll introduce an intermediate sequence, okay, xnc. So we will look at that. And we introduce this as the intermediate. So why is that? The reason is that obviously we can have this x and c converge in law to xc by our condition, right? Because c stays as c, doesn't change. Those k dimensions stays. Only those d dimensions converge, right? We have that. And we also can have that when we take the difference between this intermediate and the actual sequence, if we do that, okay, then it's basically what? It's basic because all the first d dimensions will have 0 difference. And we only have differences in the last k dimensions. And that's just equal to ym minus c by any norm you want. And that's basically it. So therefore, with this, we can actually say that the probability, okay, this difference greater than some epsilon will be equal to the probability that this difference greater than epsilon. And we know this will go down to 0 as n goes to infinity because we have ym converge in probability to c, which is implied by this yn convergent law to c. You see? So therefore, with this result, we are having that condition in theorem B. That is, okay, x and ym minus x and c converge in probability to 0. We have that. And this together with this is x and c. This intermediate sequence will converge in law to that. We're done. Okay, so we're using that previous theorem we just proved to help us prove this theorem. So you see its immediate use. Okay, so just to give you a counter example that if C is not fixed, we cannot have this result. Okay, so counter example. That is, if we have xn in law to x, yn in law to y, then jointly x and yn may not converge in law to xy. Okay, so in this counter example, let's let xn, okay, because it's an example, we can make it extreme. So just equal to x, okay, follows uniform 0 to 1. Okay, and we let ym, okay, be equal to x if n is odd, and 1 minus x if n is even. Okay, that's how we define y. So therefore, you see that ym by this definition will still has limit, right? Or actually, we can just say that the ym will always follow uniform 0 to 1 by its construction. So because it always follows uniform 0 to 1, so we can say that ym converge in law to this x as well. Well, actually, sorry, I shouldn't say this x, but it's converging to this, I should say ym converging to in law to y, any y that follows uniform 0 to 1. We can say that. Okay. But if you look at this xn, ym, what does it have? Think about it. It's based on the same x, okay? Whenever I have a realization for x, it's actually x, or x, next x, 1 minus x, next x, next x, 1 minus x. So what does it have? What's its distribution? So it doesn't converge to anything. The reason is that basically, okay, think about it. So if I draw my x, okay, to be 0.5, that's one draw. So I will have 0.5, stay at 0.5. That's okay. But if I have my x as 0.1, so 0.1, 0.1, 0.1, 0.9, 0.1, 0.1, 0.9. So that's what we'll get for one realization. And that sequence doesn't converge. And also, you see, basically, it has, the key is not that it doesn't converge, okay? Because we are talking about convergence in law. The key is that here, this y could be any y that follows uniform 0 to 1. And it has have nothing to do with this x. So therefore, if you have this construction, then you set up the dependence between xn and ym in a very arbitrary way, in this way. But this arbitrary notation y and this x may have no dependence at all. So that's why the joint distribution doesn't converge. Okay. So again, I think this is a reminder of us that convergence in law is a very weak type of convergence. It doesn't imply convergence in distribution, unless the limit is a constant. Okay, so I guess we will stop here. And so next time we will just show you that, okay, with this interesting Slutsky theorem, it gives us more tool and we can use it to derive the asymptotic distribution of the T statistic, which we use a lot in statistics. Okay, so see you on Wednesday.